Here we are going to take a look at the continuous time LTI system stability. Here's a definition for states. When a system tends to remain in a particular condition or state for an indefinite amount of time, we say that it's an equilibrium state. Equilibrium states can be classified as follows. Stable equilibrium, the system will return to this equilibrium state if disturbed. Unstable equilibrium, the system will move further and further away from the equilibrium state if disturbed. Neutral equilibrium, the system will neither go back to its original state or continue to move further away from this state if disturbed. Definition: stability. For an LTI system, we define stability as follows. Stable, the system returns to its zero state if disturbed. This implies that the characteristic modes must go to zero as t approaches infinity. Unstable, the characteristic mode grow without bound as t approaches infinity. Marginally stable, the zero input response remains bounded but approaches a constant non-zero value or oscillates with a constant amplitude as t approaches infinity. We can determine system stability by examining the location of the system characteristic equation, roots in the complex plane. Stable, an LTI system is stable if and only if all its characteristic roots are in the LHP. The roots can be simple or repeated. This type of system is also called asymptotically stable. Unstable, an LTI system is unstable if one or both of the following are true. At least one root is in the RHP. There are repeated roots on the imaginary axis. Marginally stable, an LTI system is marginally stable if and only if there are no roots on the imaginary axis. Fiber stable, a system bounded input, bounded output, stable if and only if bounded input produces a bounded output. If a stable LTI system, this is always true. Okay, here we have the complex plane, and here we have a real axis and imaginary axis. This is real axis, x-axis real axis, y-axis imaginary. And if the real axis is less than 0, that is a stable. If the real axis is greater than 0, that's unstable. And if it's equal to 0, if the if we have a pole that is equal to 0, that's marginally stable. Now let's look at some examples. So here we have characteristic root location and 0 input response. Here we have this one in the real axis. Here you look at this real axis. If it's less than 0, that's stable. So this output here is a stable output. And then here, if it's 0, if the root is 0, the marginal if the real axis is 0, that's a marginal step. Here this is 0 right here, so this is a marginally stable 0 input response. Characteristic root location, here we have 0, but this is second order pole. So if it's first order pole, that is marginally stable, but if it's second order, that's unstable. This one is unstable right here. And the next one we have is two poles, that is when the real is less than 0, so this is stable. Okay, it's giving it stable or 0 input response, and as you move it further away, it's still stable, but the thing is, it only moves faster a little bit. Here it's eventually gonna go small, it's gonna grow small and end somewhere. Here that happens a little bit faster as you move further away, but it's stable. And here this one is marginally stable because the roots are 0. the pole sign 0 at real. So this is marginally stable. It goes like this. And if you go to this right side, now this is really positive value. This is unstable. This is the zero input response. And that's basically it for this video. I hope you guys find this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.